Since early times, man has used the soils around him for his construction materials. To drain, contain, and stabilize soft soils, he experimented with other natural materials. These worked well until the fibers decayed. As road, rail, and air traffic increased, complex design and performance demands created a need for a more permanent material to enhance and supplement the engineering properties of natural soils. Geosynthetics provide the solution for many of today's transportation requirements. Geosynthetics are planar polymeric materials used with soil or rock as an integral part of a civil engineering structure or system. Many different types of geosynthetic materials are now used in the construction, rehabilitation, and maintenance of transportation facilities. These materials are grouped into geotextiles, geogrids, geomembranes, geosynthetic clay liners, geonets, geocells, and geocomposites, combinations of two or more of these materials. Geotextiles are either woven or non-woven. Woven geotextiles are made from monofilaments, continuous filament yarns, or from slit film tapes. In the manufacture of non-woven geotextiles, continuous filaments or staple fibers are carded, blown, or otherwise laid onto a moving belt to form a loose web. The filaments or fibers are then bonded, by needle punching as shown here, or by heat or resin bonding. Geogrids, primarily used for stabilization and reinforcement, are formed by a regular network of tensile elements with apertures of sufficient size to interlock with surrounding soil particles. Geocells are three-dimensional materials which offer some structural support. Geocomposites, which combine several components, are used for erosion control. Another application is as prefabricated drainage layers. Geomembranes, geonets, and geosynthetic clay liners, GCLs, are used only occasionally in transportation systems. They are generally used in environmental containment applications and are not discussed in this video. Most geosynthetics used in civil engineering are made of extremely durable polymers and are highly resistant to chemical and biological degradation. However, geosynthetics can be sensitive to ultraviolet light, and good practice dictates exposure for a limited time only before they are covered, often called timely cover. Geosynthetics are manufactured under strict quality control requirements. Their properties are evaluated according to several standard test procedures. These include index testing of different materials for rupture resistance and tensile strength. Performance tests for soil geosynthetic friction, endurance, and hydraulic properties are generally site-specific and left to the designer. Today, much of the world geosynthetic community is working towards a world standard of quality control, ISO 9000 certification. Geosynthetics have some clear advantages in construction. They provide improved long-term performance. They allow construction on difficult sites where conventional construction methods would not be possible. They reduce the volume of construction materials required. They are easier to install than bulkier natural materials. They reduce construction time, and they result in lower construction costs. Above all, geosynthetics have proved effective. Each year, hundreds of millions of square meters of geosynthetic materials are used in civil engineering projects, and their most common use is in transportation applications. Geosynthetics serve 6 primary functions in transportation facilities: separation, reinforcement, filtration, drainage, protection, and as a moisture barrier. These functions will be illustrated in the sections that follow. In the construction of roads, highways, airfields, and railroads, geotextiles increase stability and improve performance of weak subgrade soils, primarily by separating the aggregate from the subgrade. One characteristic of low-volume roads like forest or access roads and high-volume roads during initial construction on soft subgrades is pronounced rut formation due to high axle loads of construction vehicles. Deterioration of the subgrade due to rutting causes frequent maintenance problems, reduced road effectiveness, and stresses to vehicles. It is important to keep rut formation to a minimum to prevent local shear failure and the subsequent contamination of base material. One possible way of achieving this is to increase the thickness of the base layer in order to better distribute local loads. However, increasing the thickness of the base layer also considerably increases construction costs, especially the cost of replacement fill. Use of a geosynthetic to separate, reinforce, filter, and drain reduces the thickness of fill usually required and offers numerous advantages for paved and unpaved roads. A geosynthetic used in unpaved roads reduces the aggregate requirement, maintains separation of the subgrade and select fill, helps minimize rutting, reduces the amount of select fill required, minimizes site preparation, and extends the life of the road structure. A geosynthetic used in paved roads prevents contamination of the subbase and base layer by fines, allows the use of free-draining open-graded base materials, provides stabilization by distributing the pavement load, reducing the load intensity to the subgrade, reduces the depth of excavation required to remove unsuitable subgrade materials, minimizes site preparation, and extends pavement structure life and prevents pavement failure. Placing more aggregate to add strength to the road and to provide drainage is not only an expensive remedy, but in time, soil fines from below pump up into the voids between the stones above. This reduces the strength of the aggregate. The aggregate particles at the subgrade interface are also pushed down into the soft subgrade. This phenomenon also occurs with firm subgrades, but over a longer period. A suitable geosynthetic separator placed at the interface between the aggregate base course and the subgrade can prevent the two layers intermixing. Geogrids and geotextiles provide base reinforcement through one or more of these three reinforcing mechanisms. By providing lateral restraint of the base and subgrade, by increasing the system bearing capacity, and by offering tension membrane support of the wheel loads. When wheel loads are applied to a subgrade, the aggregate tends to move laterally, causing ruts in the aggregate and also in the subgrade. A geogrid with good interlocking capabilities, or a geotextile with good frictional properties, can provide tensile resistance to this movement. Geosynthetic reinforcement also increases the bearing capacity of the roadway by distributing the load over a wider area, thereby reducing the unit stress to the subgrade. The third mechanism, membrane-type support, occurs only if enough tensile stress is induced to cause the material to elongate under load. This will only happen if wheel path rutting is at least 100 millimeters in depth. This function, therefore, is generally limited to temporary roads. Pavements have less tensile strength than compressive strength. Therefore, over time, heavy traffic loading causes them to deform and crack, even if the subgrade is not especially weak. Geogrids have been shown to have their greatest reinforcing effect when embedded in the lower half to 3/4 of the pavement thickness. This is because tensile stresses are higher at the bottom of the layer. In North America, the largest application of geosynthetics, about 100 million square meters per year, is for separation and reinforcement. Their second greatest application, about 85 million square meters, is their incorporation into pavement overlays. These fatigue cracks are largely caused by traffic loading, but are aggravated by low temperatures and any lateral instability in the pavement or subgrade. Left untreated, this cracking causes roads and runways to deteriorate rapidly as water infiltrates the subgrade, reducing the life of the pavement. Overlays are traditionally used to cover cracks and provide an improved driving surface. However, a chronic problem is that old cracks reflect up through the new surface layer. Geosynthetics do not prevent reflection cracking. However, they can retard it in two main ways: by waterproofing and by local reinforcement. If properly sealed with a waterproof coating, non-woven geotextiles can inhibit the infiltration of surface water. An asphaltic material is sprayed over the existing pavement, and the non-woven geotextile is laid before the asphalt has cooled and lost tackiness. The hot mix overlay is then placed directly on the geotextile, saturating the material to provide a waterproof barrier layer. It's then rolled while the asphalt is still hot to compact the overlay. Here in Europe, a flexible grid is being used to retard reflective cracking, primarily by acting as a reinforcing element. It is firmly anchored to remove slack so that tensile strength is immediately mobilized and then tensioned before the asphalt is placed. Several wheel widths should be allowed on either side of the vehicle path. This polyester geogrid can withstand asphalt laying temperatures of 190 degrees Celsius. Drainable pavement systems combine a geosynthetic separator placed between subbase and permeable base, and an edge drain pipe surrounded by a geotextile filter. This system removes infiltrated surface water, which cannot be prevented from entering the pavement structure. Railroad tracks are a punishing environment for any material, natural or geosynthetic. The vibration caused by heavy wheel loads on rail tracks creates a pumping action which forces the subgrade up into the stone ballast supporting the ties. Traditionally, a sand layer was used to reduce this pumping. Now, geotextile filters and separators and reinforcing geogrids assist in solving the problem. They can stabilize the ballast and reinforce the track, both in new construction and track rehabilitation. This was the condition of the subgrade on a Midwest railroad in the U.S. before a geotextile was installed. To ensure survivability of the geotextile, it was placed under a thick layer of sand. The base was then finished for the tracks to be relaid. Where there is a need to reinforce the subgrade of a railroad, geogrids can act as a load-bearing platform for the subbase. They confine the ballast against lateral movement and settlement. A combination of bidirectional geogrids and geotextile filter separators can extend the life of the ballast and the track. Geosynthetics can be used to reinforce soils on soft foundations, soil slopes, and earth walls. Load is transferred from the soil to the geosynthetics, which restrict movements by mobilizing tensile strength. Constructing an embankment on poor soil is essentially a problem of bearing capacity and deformation. Failures of embankments in these situations can be dramatic and are expensive to repair. Embankments, dikes, or levees constructed over silts, clay, or peat layers tend to spread laterally because of vertical earth pressures acting on the base. Geosynthetic reinforcements used to increase stability are usually placed with the strong direction perpendicular to the center line. A geotextile or geogrid resists lateral displacement. Reinforcements may also be required to bridge over local weak areas or voids, as in karst or thermokarst topography. In this case, tensile reinforcement may be needed in more than one direction. In the early 1980s, a new runway extension was created for Washington's National Airport. It was constructed on an embankment section founded on soft marine deposits. For this project, a high-strength geotextile had to be specially manufactured. Once the lengths were seamed together, it covered an area the size of 3 city blocks. The accordion-folded fabric mat was towed into the river, spread out, and stretched in place over the river bottom to provide a base for the new embankment. The alternative would have been to excavate large quantities of soft, unsuitable material and replace it with more substantial fill. This would have been much more costly and environmentally unpopular. It would also have taken about 3 years, whereas it took less than 100 days to provide the airport with a geotextile reinforced embankment for the runway extension. From soft foundation soils, we now move to the reinforcement of steep embankments and slopes. Multiple layers of geotextiles or geogrids may be placed in new or reconstructed slopes to reinforce the soil and to increase slope stability. This is the technique demonstrated here in the reconstruction of a section of highway near the Idaho-Montana border. The embankment was constructed using 300-millimeter layers of backfill from on-site roadway excavation. A geotextile composite reinforcement material was placed between each soil layer with its strongest direction perpendicular to the embankment alignment. Construction equipment was not permitted directly on the geotextile. A temporary form was used to support the face of the embankment during construction. This was done to minimize movement during compaction and to maintain the angle required on the face of each lift. To give the face of the embankment a tight and smooth surface, a windrow was formed behind the face. The tail of the geotextile was then lapped back into the windrow. A dozer carefully leveled material over the lap, anchoring the material in place. These details permit equipment to work close to the edge, so the soil can be compacted more thoroughly. This improves the stability of the edge, reducing sloughing. Once the slope was completed, an erosion control matting was applied to protect the face and to provide a platform for hydro-mulching. Geosynthetics used in this manner can bring significant economies. They reduce the volume of fill required. They can create a usable area at the toe of the slope or at the crest. They require no specialist labor or equipment. They remain stable during construction. And they allow the use of local backfill. And backfill can represent 80% of the total cost of the slope. The design analysis of steep slopes is, of course, critical. If the reinforcement fails, the slope will fail. The same applies to mechanically stabilized earth walls. Retaining walls in transportation engineering are required where a slope is uneconomic or technically unfeasible. Mechanically stabilized earth walls, MSE walls, contain some type of reinforcing elements in the soil to help resist lateral earth pressures. For nearly 20 years, geosynthetics have been used as a viable and economical reinforcing element in vertical or near-vertical walls. A geotextile transfers stress to the soil through friction on its complete upper and lower surfaces. Geogrids transfer stress to the soil through passive soil resistance on the grid's transverse ribs and through friction between the soil and the grid's longitudinal ribs. Geosynthetic reinforced walls can be faced in a variety of ways, with wraparound facings, with gabions separated from the backfill by a geotextile filter, with full-height precast or cast-in-place concrete panels, with timber facings, or with modular concrete units now produced in a variety of attractive forms. We have already seen geotextiles used as wraparound facings for a steep slope. They are used similarly for geosynthetic reinforced MSE walls. Geogrids are also used for wrap facings, though some kind of covering or vegetation is needed to prevent the fill soil from passing through the grid apertures. In crowded Japanese cities, to save space, railroads are frequently built on embankments of geosynthetic reinforced soil. Here we see gabions of bagged gravel wrapped in layers of geogrid, backfilled with local soil. These flexible walls are often faced with concrete panels. Modular concrete units, MCUs, are now by far the most popular geosynthetic wall facings. They are relatively easy to construct and offer a range of aesthetically pleasing finishes. Units are connected one above the other with pins or lips, or in this case with geosynthetic connectors. The strength of the connection must be addressed in design and can control the maximum tensile load in a given layer of reinforcement. Geosynthetic reinforced walls are flexible, which makes them attractive for earthquake zones. During the Great Kobe earthquake of January 1995, many conventional masonry and reinforced concrete gravity-type retaining walls totally collapsed. Many modern cantilever reinforced concrete walls were also seriously damaged by excessive tilting. Geogrid reinforced walls with full-height concrete facing performed well despite the devastation around them. So far, we've looked at the separation and reinforcement functions of geosynthetics in transportation applications. It's time now to focus on two other important functions: filtration and drainage. For filtration, flow is cross-plane, through the geotextile, not within it. Whereas for drainage, flow is within the plane of the geosynthetic. Geotextiles are effective, economical, and easy-to-install alternatives to granular filters in applications involving the flow of liquids. Geotextile filters are used around trench drains and pavement edge drains to prevent soil from migrating into the drainage aggregate while allowing water to escape from the soil. Beneath pavement permeable bases, blanket drains, and base courses. As drains for structures such as retaining walls to separate the drainage aggregate or system from the backfill while allowing free flow of ground and infiltration water. And as wraps around slotted or jointed drain pipe to prevent drainage aggregate from entering the pipe while allowing the free flow of water into the pipe. As with filtration soils, a geotextile is assessed according to the extent to which it retains soil particles while allowing water to pass through freely throughout the life of the system. The pore sizes in the geotextile must be neither too small nor too large for the soil it is filtering. The geotextile must have the correct porometry to force the upstream soil to accommodate the required flow condition. Both the project design and the filter design are critical issues. Many geocomposites are specifically designed for in-plane flow of water. They may be prefabricated or fabricated on site. Prefabricated geocomposite drains are readily available materials with known filtration and hydraulic flow properties. As they are easy to install, they also offer construction economies. These materials consist of a geotextile filter separator bonded to a stiff or flexible drainage core. All have high flow capacities when they are not compressed, but differ in their compressed state. Most manufacturers quote the flow rates under load and at various gradients. Geocomposite drains are used in three main ways: as edge drains for pavements and interceptor trenches adjacent to roadways, as sheet or blanket drains, and as vertical or wick drains. Here, a prefabricated geocomposite edge drain is being positioned to carry water from the base course of the highway. Good connections with overlapped geotextile splices are critical to prevent soil infiltration. A continuous trenching machine followed by a traveling boot device allows the drainage material to be placed to the correct depth and slope. The narrow trench is backfilled and compacted, and the drain is then tied into the collector drainage system. Sheet drains, placed behind abutments or retaining walls, are an integral and critical part of the wall system and must be designed to last the life of the structure. The drainage composite must accept a calculated seepage flow from the backfill, while the geotextile must provide adequate filtration without clogging or causing piping in the soil. Here we see a drainage layer placed between the ballast and subbase below a rail track. It collects and drains water from the underlying subgrade and the ballast above. Composite wick drains are inserted vertically into the foundation soils to consolidate saturated soils like clays and silts. The pore water, under pressure exerted by the surcharge load, is forced upwards through the drains. A metal plate or shoe is attached to the drainage wick protruding from the bottom end of the piercing device. The wick is installed to the required depth via the lance and left in position below ground. The lance is then extracted and the end of the drainage wick cut off. The drain is a water-conducting core covered with a non-woven geotextile acting as a filter separator. The water forced up the wick drain by the surcharge load can be pumped off or can be gravity drained from the site. The time it takes for the subsoil to consolidate is the key design issue. The applications we've seen so far demonstrated the primary functions of geosynthetics. In this section, we turn to applications in erosion and sediment control, where the primary function is not so easily identified. Soil erosion, largely caused by the impact of rainfall and the flow action of streams and rivers, threatens the stability of roads and railroads and their slopes and embankments. Geosynthetics fulfill multiple functions in controlling erosion. These have been divided into two basic categories, sometimes described as terms, temporary measures, and PERMs, permanent erosion control measures. As terms, soil retention blankets or mats made of both natural and synthetic grids, meshes, nets, fibers, and webbings can provide tractive resistance and reduce water velocity on slopes. These products retain seeds, some are pre-seeded, and add a mulch effect to promote the vegetation that will be the permanent erosion control. The blankets degrade after a period. As PERMs, a variety of geosynthetic materials are used in different ways. Geotextiles held in place by pins or riprap can be used in ditches, culvert outfalls, or on embankment slopes. More robust geosynthetic mats support plants whose roots become entangled in the mesh. These reinforcements last for extended periods. Where some structural support is required, flexible webs or cells are filled with soil. The three-dimensional cells confine and reinforce the soil, allowing normal drainage but holding the infill in place. They can then be vegetated to give the native cover which controls the erosion. Geosynthetic cell structures can also be filled with crushed gravel, forming a reinforced mattress for improved bearing capacity. Geotextiles have long been used as filters beneath permanent hard armor systems of riprap, concrete interlocking blocks, gabions, or geosynthetic forms filled with grout. Soil loss during construction can be temporarily arrested by using geosynthetic materials. Geotextile silt fences placed downslope from a construction site can trap sediment suspended in the runoff while allowing the clear water to pass through. In a similar application in water, a geotextile turbidity curtain will reduce water velocity, trapping the sediment and allowing the clean water through. This prevents water disturbance and contamination outside the construction area. With hundreds of geosynthetics with different properties now available, selecting the appropriate material for a particular project isn't easy. Geosynthetics are engineering materials. They are designed and tested according to standard procedures in the same way as other materials. Many conference papers, publications, studies, and books have been developed over the past 20 years. This body of knowledge provides well-documented design and construction methods and real evidence that these materials work. All designs should be site and product specific. The final factor of safety will depend on an evaluation of critical versus non-critical and permanent versus temporary criteria. The non-critical temporary situation will have the lowest factor of safety, and of course, the permanent critical the highest. Once the design has been formulated, a detailed set of plans and specifications will be drawn up for a specific project. These should include index properties reported in minimum average roll value units, MARV units, specific performance properties, seam and overlap requirements, acceptance and rejection criteria for sampling and testing, general requirements about the selected material with instructions for its storage and handling, maximum time allowed for exposure to UV light before backfilling, placement procedures, grading and ground clearing, aggregate specifications and lift thickness, and the type and weight of equipment to be used, and repair procedures for damaged sections. Without proper construction quality control in the field, the best designs and the best materials can fail. Geosynthetics must be stored and handled with care and must be installed correctly. Both factory and field-seamed geotextiles should be inspected for thread type and tension, stitch density and type. To evaluate the nature of the subgrade and covering soils, geosynthetics should be inspected for damage by clearing a test area or by constructing a trial installation. As a part of quality control and quality assurance, a test pad is an excellent way of testing the installation survivability of a material. Geosynthetics have been successfully used in thousands and thousands of transportation applications. For numerous functions and applications, they continue to be a cost-effective option. Geosynthetics technology is a proven, mature technology which meets standard requirements of design and testing. Geosynthetic materials have been shown to be durable and reliable in long-term use. What is more, they have made construction possible on sites thought impossible until now. With new products and new designs continually developing, geosynthetics are guaranteed a place among the most significant engineering materials of the future for transportation facilities the world over.